his work mainly focused on silicon and silicon carbide and gallium nitride on silicon devices, and more recently on diamond power diodes. And currently is the head of the wide bandgap superconductor devices group in that institute. And he also, more recently, is also working on carbon-based material for nanotechnology and biosensors. And today he will talk us about semiconductor devices at high temperature and their application in space for space missions. So Philippe, you can, I leave you the stage, and if you want, you can share the slides.
Okay, thank you very much for the introduction. So I will share my screen. Okay, you can see it?
Yes.
Okay, great. So thank you very much for inviting me to give this talk in this pizza seminar. I was about to ask why this name, so now I got the answer in this introduction we get before. So I think it's a very nice initiative, and I hope one day I can also participate. So today I want to talk about the procedure we have follow here at IMB-CNM in order to develop a semiconductor device for a specific application in the Pepe Colombo mission. So it will basically deal with semiconductor for electronics. Okay. So as you know, in our daily life, but also in space life, we are fully surrounded by electronic systems. And this is a very large part of our current society. And in space, so you can have a spacecraft and satellites full of this electronic, but most of the electronic is developed for terrestrial application. And when you go to space, you find quite different ambient and operation condition, which oblige you to adapt all your electronic systems to this environment. So specifically, which are the main constraints in space for electronic systems compared with terrestrial application? We have first a high exposition to radiation. We have also high mechanical and vibration stress, especially during the launch phase of the satellite, of the payload. All these electronics must work with a limited energy supply, which is typically provided by solar panels. We also have limitation in the weight and volume of all the system. Another aspect is the vacuum. All this electronic work vacuum, which will difficult all the aspects of thermal management and thermal dissipation, and which may also generate some outgassing of given materials. In some mission also, as the one we will talk about later on, we have high and low temperature condition for these electronics to deal with. And finally, you need a very high reliability of all your system, because obviously it's quite difficult to go to repair or substitute parts which may fail during the missions. So just electronic systems are typically composed of different components, like passive components, like capacitors, resistors, inductance. These components typically depend essentially on temperature and mechanical stress. Then you have the active components, which are basically based on semiconductor components, like microprocessor, for instance. These active components, semiconductor components, are very sensible to radiation and to temperature ambient also. And finally, we have all the surrounding components for interconnection and PCB boards, which them are more sensible to mechanical stress and also to temperature as usual. So focusing on semiconductor, as you may know, most of the semiconductor devices you can have and you can use in all the electronic system you have around you are based on silicon as semiconductor. Silicon has several advantages. Cheap, this is one big advantage for the industry, but it's also a material which is quite common, and you can get very high quality of material with very low defect density, which is important to build electronic devices. Another very good advantage is that it has a natural high quality dielectric, which is almost compulsory to build any kind of electronic substructure. One of the physical parameter which is usually very relevant for a semiconductor is so-called wide bandgap width. This wide bandgap will impact a lot of performances of your semiconductor, especially in electric field capability, in temperature capability, and also in radiation hardness. So the gap of silicon is 1.12 electron volts. So let's say it's that kind of reference. So you have other semiconductor that you can find in your application, which are germanium, for instance, which have a lower gap, or 3-5 semiconductor like gallium arsenide, indium phosphide. So with this material, you can play and you can get a wide range of gap between 0.3 and 1.5, which allow you to do so-called heterojunction devices, which are especially interesting for telecommunication components or very high frequency components. And more recently, you have heard about new two-dimension materials. The most famous is graphene, but graphene have a gap of 0 electron volts. So it's not really a semiconductor. You cannot build a transistor with graphene, with pure graphene. This is why now you have many research oriented to other 2D material, like molybdenum disulfide, which have a gap more similar to a standard semiconductor, and then could be used to build some electronics functions. And in the last 15 years, a new family of semiconductors exhibit a very an exponential growth. These are the wide bandgap semiconductor. So like silicon carbide and gallium nitride, which are now commercially available, which have a gap around 3 electron volts. And for the next generation would be the ultra wide bandgap semiconductors with gap higher than 5. So it's diamond, aluminum nitride, gallium oxide. So all these materials present superior characteristics to silicon for given application, especially for high voltage operation, for high temperature application, and also for high frequency devices. For instance, they are already used in existing application, like for telecommunication, for 4G and 5G is based strongly based on gallium nitride, for instance. Also new application about electric transport, electric car, electric plane, also use a lot of this wide bandgap semiconductor, renewable energy, smart grid, which is the next generation of energy distribution systems, are already using these materials. So again, as I said before, semiconductors are especially sensitive to radiation. And this is important for space application. And you have typically 2 kinds of degradation generated by some radiation impact on semiconductor. One is the cumulative effect. So it's based on the dose, cumulative dose of particles that the device will receive, and which will create a progressive drift of the electrical parameters. And the other one, the other phenomena is single event effect, which is sometimes caused only by one particle, but we may cause, in the best case, some data loss, for example, in a memory, but usually generate directly a device destruction. So, for instance, in the bottom picture, you can see the top view of, on the left side, the top view of a device. And you can see that in this red circle that there is something wrong in this device after a single event defect. And if you do a cross section of this device, so you do a hole inside and you look transversally of this device, this is the right picture, you can see that you have a metallic layer, an aluminum layer, where you have a big hole, but indeed in the bottom layer, which is the silicon, the semiconductor layer, you also have a very big void. So obviously this device is not working properly anymore, and it was caused by probably only one particle effect. So we have to deal with this, especially so for application in the energy field or in the space application. So I will then, based on this introduction, explain what was an overview of the whole process we have performed in order to develop a specific semiconductor device for the Bepi-Colombo mission. It's a protection device for solar panel, which have been ordered by European Space Agency for this mission. So just a reminder, but probably you know much better than me this mission. The Bepi-Colombo mission is targeting to study Mercury planet. So there are a lot of unknown parameters about Mercury. For instance, it seems that there is an unexpected magnetic field. There is an atmosphere with some proportion of different elements like potassium, calcium, magnesium. There are also some observation of depression of the surface from a known origin, and it seems also that Mercury is shrinking. So there was a joint effort between the European Space Agency and the Japanese Space Agency to build a new exploration mission named Bepi-Colombo. So the Bepi-Colombo came from the name of a famous astronomer, an Italian astronomer, which was apparently a great expert of Mercury. So the mission was launched in 2018, but the original date was more in 2013. So there was like a 5 years delay in the launch. The mission, the final position of the orbiter will be in 2025, when they will start to do the study. So the spacecraft is still doing some gravity assist maneuver in order to reach its optimal orbit around Mercury. So the end of the nominal mission is scheduled in May 2027, but they expect to be able to work a bit more if all the systems survives, at least 1 year more, up to 2028. So the mission is composed of two satellites. One developed by the Japanese, which is basically to study the magnetic field of the planet. It's a MMO. And the other one developed in ESA and to which we participate is a Mercury planetary orbiter, which will study other aspects of the planet I mentioned before. So of course, Mercury is very near from Sun, as you know, and we are working in very harsh environment, especially in terms of radiation and temperature. And indeed, in this mission, almost 80% of the different parts needed to build the spacecraft were specifically developed for the mission. This is also why, what explains why the mission was delayed 5 years, because it was a very big challenge in terms of research and development and technology. So from our side, we have developed a very small component, which is a protection device used on the solar panel. So obviously, this device will be in the worst condition of the mission because the solar panel is not directly, but partially exposed to the sun. So the temperature on the solar panel will be the hottest point of the satellite. So why this device? Typically, a solar panel is made with solar cells which are mounted in series, and then you have a row of solar cells which are in parallel. So if you one of the solar cell or solar cell rows is damaged, for instance, by a radiation event, you may have a short circuit in this row. And if you have a short circuit in one of these rows, which is in parallel with the other one, all the power, all the current generated by the other cells will flow through this short circuit. And then your satellite or all your electrical system of your satellite will not be supplied anymore by the energy of the solar panel. So here you need to add a simple component, a protection component, which is called blocking diodes, which is in series with the row, and which will protect in case of damage of one of the row to avoid that all the energy produced by the other cells go in this row and still supply all the electronic system of your spacecraft. Yep. So the project was done in different phases. And the first phase, of course, is to define the specification of the mission and of the device. So we have, in this case, known parameters, which are basically the electrical parameter of the system, which is the current, the power needed for the system. But in the case of Mercury, we have also a lot of unknown parameters, which are the ambient parameters, especially the maximum and minimum temperature seen by the different parts, the radiation doses. So here there was an initial work from ESA people with their partner to model and to simulate which will be the condition and the mission profiles for all the electronics of the MMO. And for us, what was important was the temperature cycle seen by the solar panel. So again, the ESA had to made an estimation. There was a lot of discussion and change in the parameters. But finally, the setup and fix that the minimum and maximum temperature seen by the panel would be between minus 165 and plus 230. And moreover, as they add a safety margin, they consider that the electronic of the solar panel would see as an external temperature between minus 175 and plus 265 degrees. So this temperature is by far out of the possibility of silicon semiconductor, for instance. So finally, they define the final specification of the device we had to produce. The main one being the 3 amps of current, 300 volts of voltage capability, a junction temperature, which means the temperature inside the device of 300 degrees C, and there were also constraints on the weight of the device. So once they define the different specification, then they have to find the device, so the component. So there are 3 options. You can either use existing space qualified components, which are in the ESA list of provider. So these components are already qualified for space application. So you can use them almost directly in your system. The second solution is to use commercial components which have been developed for terrestrial application. like for automotive, which is also quite stringent condition. So in this case, you have to demonstrate that this component fulfill with the standards of ESA. So you have to do a qualification test campaign of the component in order to demonstrate that these devices can be used for space application. And if you don't find in this solution the right component, then you have to develop it from scratch. And that was the case of this specific high temperature component for solar panel. And we were chosen by ESA to develop these devices as a specialist of wide bandgap semiconductors. So our work starts here, and so the first discussion was to select the optimal semiconductor. So we select to use silicon carbide, as it's expected to have high temperature and high radiation capability. This material is, you cannot find it naturally on Earth. It's a synthetic material, even if it's only silicon and carbon combination. It's grown by a method called sublimation, which makes that you obtain this ball that you can see on the left side picture. It's a small ingot in form of ball. And from this ingot, the manufacturer will dice a very thin disk of semiconductor, so what we call a wafer. You can see it on the right side. And it will generate several wafers from this ball. On silicon, these balls are much larger, so you can get much more wafer from one growth, which makes that silicon is much cheaper than silicon carbide. And this is really, the cost is really the main limitation for a wide use of silicon carbide in electronics in general. So once we decide which material we use, then we start with design phase of the device. So using commercial device, we do modeling of the internal structure. We define geometries of the component in order to fit with the specification which are required by the customer. We draw the photolithographic masks which are needed for the fabrication. So after this phase, we have to purchase the starting material, so the wafer I showed before, coming from this ball. And we start with the fabrication in the clean room, so which is a very big building you may see if you enter in the university through the science entrance. Below our building, we have a very big red building where we can do this fabrication. So I have a short video, 3-minute video showing the clean room, and I hope it will start properly. Can you listen?
La sala blanca del IMB es una sala muy versátil y en ella se fabrican dispositivos de tipos muy diferentes, desde sensores de gases, detectores de radiación, biosensores, etc. Cada uno de estos dispositivos tiene unas peculiaridades a la hora de su fabricación y por tanto cada vez un nuevo dispositivo presenta un nuevo reto tecnológico. Para el personal que trabaja en la sala blanca, yo creo que es muy interesante y gratificante porque no se trata de hacer un trabajo monótono y siempre las mismas etapas estándar, sino que hace que tengas que estar siempre un paso más allá, pues intentando solucionar problemas que aparecen en la fabricación, poniendo a punto una nueva técnica, siempre al día y actualizándote, y para ayudar a que estos dispositivos lleguen a buen fin.
La Sala Blanca principalmente se dirige a investigadores, especialmente, primordialmente a los propios investigadores del Centro Nacional de Microelectrónica, pero también está abierta a pequeña y mediana empresa para desarrollar pequeñas series de prototipos y favorecerles el poder tener contacto con estas micro y nanotecnologías, ya sea porque ellos tienen el conocimiento o de la mano de nuestros investigadores que les pueden facilitar ese acceso a tecnologías innovadoras.
Es muy gratificante que estos dispositivos lleguen al final a buen puerto y haber podido participar en colaboración con los investigadores, pues ofreciendo toda tu experiencia y pues tu entusiasmo también a la hora de preparar nuevas técnicas o bueno, volcarte en nuevos dispositivos. Para mí es quizás lo que más me gusta de trabajar en este campo y concretamente en el área de microsistemas de la Sala Blanca del IMB.
Okay, so you have seen that the working conditions are a bit special. We did a very controlled ambient in order to be able to integrate all these electronics devices with high precision. So once we have produced the wafer, we start with characterization, and we first measure on wafer to make a first selection of devices. So we use this kind of equipment, which are wafer probers with tiny probes in order to contact and to be able to apply electrical signal. And we test one by one all the devices of one wafer. So this is a procedure we call a mapping, and it's done to do a first screening of the good working devices on the wafer. So an ideal yield, a good yield would be between 85 and 95% of good device on the wafer. You have, for example, forward characteristic of a full wafer, of all the device of a full wafer, and you can see that there is a, let's say, a group of standard characteristics, and some of the characteristics are out of specs. So definitively, this device will not be compliant for further processing. So typically, we draw the wafer and we identify which are the good devices, for instance, here in green, and we only use these green devices for the next steps. So the next steps is the packaging. So first, we will dice the wafers in order to get individual chips. So the devices are separated one from the others, but we cannot use the devices like this in a real world. You need to interface the device with the real world, and for that we use packaging. So we put the device inside a kind of box with pins, with interconnections. And this is also an important part of the development. So not only the pure semiconductor die is important to optimize, but also the packaging, because if the packaging is not fully in line with the die, you will not take profit of the performance of the die. So in the case of the device, the packaging has the same constraint as the die. So a very good mechanical resistance, a good thermal dissipation, a reliable electrical connection, and especially high temperature capability. So for that, we again develop a specific package for this component. starting with the backside soldering. So we have to stick the die on the base plate. And for this, we use solder alloy. So we optimize the solder alloy and we choose gold germanium, which is not commonly used in industry because the process is very difficult, repetitivity is very difficult to control. But in our case, we were able to have a reliable process with a good repetitivity. And to check this process, we use a scanning acoustic microscope that you can see the results. So we make a picture of the interface between the die and the substrate. And if you see here this white area, it corresponds to air which is present between the die and the package. So this air will affect a lot the performance of the device. So this is a wrong, let's say, wrong result, and the good result is the right one, where you see that the voids between the die and the package are very few. We have only two small white dots. So in this case, the device can be considered as okay. Another step is the topside interconnection of the component. So originally we have used the typical wiring system. So we use aluminum wire, but definitively with the high thermal stress and cycle we need for the Bepi-Colombo mission, this wire were not able to sustain the stress and the lift after a given time of stress. So we had to switch to a different solution, which was to use gold wire with a smaller diameter and to put more wire in parallel. And indeed, gold on gold solder is really the perfect solution, especially if you have high temperature cycling. Obviously, due to the cost, it's not something that is used in standard application, but for a specific application like this one, it was suitable to use this solution. And finally, we have to close the package. And importantly, to avoid to have oxygen inside the package, especially if we will have heating of the device, because we may have some oxidation of the surface. This is why we close hermetically the package, and the package is filled inside with nitrogen. Okay, so after this packaging phase, we have let's say the final component ready. And then we have to check, after all these steps of processing, if the component is still proper for the application. And we have to go through a so-called screening or burning phase. So all the parts must follow this stress. We have each stress is defined for each kind of device. So in our case, we use this 150 degrees C, 48 hours biasing at 300 volts in order to try to see some defects inside the produced devices. And for instance, in this device, we observe that we had a hotspot on the periphery of the component in this red circle, which damaged the component. So we discard the use of this component. So all the devices which pass this burning phase then can be used for the qualification test and the test campaign as the next step for the application. So this is the phase 3. It's a test campaign in order to demonstrate and to qualify the component for the application. So this is defined between the European Space Agency and the customer and the manufacturer. And you can see that we made a lot of different tests, both for environmental, mechanical endurance, assembly, radiation capability of the component. And obviously, we do the test on a sufficient number of devices to get a good statistic and a representative statistic of the behavior of the components. So this has been mainly done in Altair, which is a company specialized in this kind of qualification test for space and automotive in Madrid. From all these tests, important was the radiation test. So in the test plan, we had two kinds of radiation tests. One was the TID, the total ionizing radiation dose. So ESA calculates that the dose, radiation dose received by the element during the mission would be around 39 kilorad. If considering a 1 year more mission, it would be 42 kilorads. So ESA, as usual, apply safety margins, so they multiply by 2. So they ask us for a final gamma dose, a minimum gamma dose of 84 kilorad for the devices. So we test the devices, and we went much above these limits. We test up to 570 kilorads, and we didn't observe any degradation of our device. So confirming in this sense that silicon carbide was optimal for this case. We had pretty similar results with proton irradiation done at different energies and their biasing. Again, we had a very small drift of our characteristics, and indeed the drift was in the positive side, meaning that after proton irradiation, the device were slightly better than before. However, during this development phase, NASA published a paper showing that we could have an issue with heavy ions on silicon carbide devices. So it was really new information, and this test was not originally scheduled in the test campaign, but we finally decided to test our devices under heavy ions. And effectively, we have seen that we had a kind of premature degradation, so a breakdown at 250 volts, while our devices are target 300 volts, under a relatively medium LET, so energy dose of 32 of heavy ions. So it confirms that effectively silicon carbide is quite sensitive to heavy ions. It was not considered as critical for this mission by ESA, so we were able to pursue our test. But definitively, this heavy ions issue is today the main limitation for a wider adoption of silicon carbide in space application. And we are trying to solve this problem, working on the design and the technology of the devices to improve this heavy ions resistance. So among all the tests I show, the most extreme and critical was the temperature cycling test. So as I said, European Space Agency defined a temperature emission profile for the solar panel with a wide range of temperature excursion. As I said, silicon cannot definitively not sustain this temperature cycling. And we test then our devices with 4,000 thermal cycle between -175 and 265 under a forward current DC bias of 5 amps, and with quite stringent conditions also of temperature gradients for electronics. And after this 4,000 thermal cycle, it took more than 3 months test. It's quite long evaluation. We didn't see any drift of the electrical characteristics, so it was quite very good results. ESA was very aware of what could happen with this test. because there was no previous experience on that. And definitively, this test was the final test to validate our device and to obtain the qualification to have our device considered as flight devices, flight qualified devices. So after all the test campaign and qualification campaign successful results, we start with the production and delivery of the final devices to the Airbus, who was the manufacturer who assembles the solar panel. So here you have an example. It was a test solar panel in order to check also all the interconnection. So you can see in the red circle our devices and all the solar cells row, different solar cell rows. So this sample was mainly to make mechanical tests to see if all the interconnection cables were withstanding the harsh condition of mechanical vibration. So we were happy because our work was supposed to finish here, but we had a last issue because the solar panel manufacturer made an extra test, which was not scheduled by European Space Agency. They apply a high voltage on the case of the package and apply temperature and vacuum cycling. And after this test, they observed that 3 of the devices among the 720 which were mounted on the panel failed. So it was a big issue, a big panic, let's say, since this was non-expected, but quite important issue. So we were asked to urgently make an extensive analysis of the failure to try to understand and analyze if it was relevant or not for the final application. So the best way we had to analyze it was to use locking thermography. Thermography imaging of the top, you see the top of the device by thermography, which allow us to identify a hotspot on the failing device. And again, doing a cross section in this in the area of this hotspot, we could see that there was effectively an important problem that the metal lift from the surface of the silicon carbide, creating this damage. So once we identify where was the problem, we also made a lot of meetings with different partners, tried to understand what happened. And we came to the conclusion that we had an electrical arcing between the internal wires, so that you can see on the left picture, and the top lead of the package. So why we didn't detect that in our standard test? Because we perform this isolation test at room temperature and at atmospheric pressure. But when you decrease the temperature and you decrease the pressure, the minimum distance needed for having an arcing between 2 electrodes is increasing. So you can have an arcing under these low temperature and low pressure conditions that you will not observe in, let's say, the standard atmospheric and room temperature conditions. So after this analysis, we apply mitigation actions, which were basically, of course, to substitute the failed parts. And ESA decided that this condition, which were used by the manufacturer, were not indeed realistic for the mission. They applied too much voltage that this voltage will not be seen during the mission. It's not it's not inside the limitation of the mission profiles. So apparently the risk is limited, and moreover, almost all the parts also pass the test. So they were confident that there will be no more problems. But this again delayed the integration of the devices on the final panel. So then finally, the panel was fully assembled. It was assembled to the spacecraft. They made a test of the opening panel of a solar panel in 2017. And then we have been able to see the launch. So everything was okay during the launch. And also everything was okay during the opening of the panel after the launch, which is a very critical phase, as you know, since if the panel doesn't open and doesn't activate, the spacecraft will remain without any energy, so it will useless. So now everything is running around Mercury, and we are expecting to see which are the first results in 2025. So based on this development, since the component we build, despite to be a relatively classical component, it's quite specific and it's quite unique at the international level. So it was again selected for other missions, like for instance, a solar orbition mission, exactly for the same application for the solar panel, since ESA calculation shows that solar orbiter condition will be very similar for the solar panel to the ones of Bepi-Colombo. So we also produce components for this mission, and we also produce components for the JUICE mission, which is for going to Jupiter. So in this case, the component is not used for its high temperature capability. It's used for its switching performances. So it's used in a different condition of the Bepi-Colombo and solar orbiter, but they were also included inside the JUICE spacecraft. So that's it. So I would like to thank all the Bepi team, which was quite big in our center, in our development team, and all our clean room staff. And we also collaborate with Alter Technology for the qualification test, and University of Valencia and INSA Lyon for some help in characterization and packaging aspects. So thanks for your attention. And if you have any question, I would be happy to try to answer.
Thank you very much, Philippe. It was a really interesting seminar. It's very far from my expertise and my research, but it was very interesting to see all the steps of the development of this kind of devices. So are there any questions from the audience? Please raise your hand or open your microphone.
Hello, this is Luis Fonseca from IMB, so a colleague of Philippe. I just want to ask a question, if I may. You told us that in addition to different parameters that the chip should offer, there was a weight limitation. Has this posed a real problem with your approach, or it was easy to be inside this 5 grams limitation?
Yes, basically the weight limitation was fixed by the package, because obviously the semiconductor die is very light. But the package must comply with the weight, and you cannot use too much. Well, it was limiting the package size, the package thickness of the wall, which are very important for the thermal management. So the main limitation was here, and indeed the device is 4.2 grams. So we are not so far from the limitation which was asked by the customer.
And you mentioned like 700 devices. All those devices are installed in the.
Yes. We supply more devices, and on the panel you have 720 devices on the panel. Yeah. But of course, we supply more than 1,000 devices.
Mm-hmm. And what's your feeling regarding which is the weakest spot of the device, the package or the semiconductor chip? You show us that there are issues with both, but if in the end this will eventually fail after many years, you think that it will be a matter of the package or it will be a matter of the chip?
You cannot separate the package from the chip, because they are really working together, and unless you have a very, let's say, stupid failure of the package, for instance, on a metallic pin which broke due to mechanical stress, the failure will be linked between the two components of the package and the die. And that's what we have seen, for instance, with this unexpected failure observed after this test. It was the die failed because the wire bonding from the package was too near from the top lead of the package. So it's really a combine, and find a name now, but it's really a couple between the die and the package.
And the heavy ions issue is something that worries you?
It worries especially yes, NASA and the European Space Agency, because we could use silicon carbide in many other applications, but there is this issue which, let's say, really stop people to think about silicon carbide for space application. So there is recently a paper from American people, from NASA, which suggests some mitigation solution on the design of the structure, trying to reduce the maximum electric field in the structure, which would mitigate the impact of the heavy ions. So we could work in this direction in order to solve or to improve the problem.
I assume that ESA at some point said that it's not that critical for the Bepi Colombo mission, this issue, and I guess it's the same for the other two that you mentioned, no?
Yes, of course. They are aware of the results. They are included in the reports, and the same people manage this component in ESA, so they are aware of the limitation, but they consider that it was not the limit we obtained was not critical for this application, because they asked for us for a 300 volt devices, but in fact, again, they apply a very high safety margin. So the voltage, the maximum voltage probably seen inside the solar panel will be around 120 volts. So more than half the voltage where we can start to observe this degradation due to heavy ions.
Thank you very much.
Any other questions? I don't see any raised hand. Maybe I have a question. Are there any prospect for use this kind of device in a non-space application in extreme condition? I don't know, I think, for example, tokamak for nuclear fusion, where you expect to have a high temperature and high radiation.
Absolutely. We are now developing different kind of radiation detectors for application like fusion, for some also from nuclear application, also for the new experiment in CERN. They will increase a lot the doses of particles in the large hadron collider, the new one, which will start to work in some years. And the current silicon detectors they use cannot withstand all the level of doses of particles which are planned to be used in these new experiments. So they are looking for alternative like silicon carbide or diamond. Diamond is also a very nice material for this high temperature, high radiation detection application. So definitively, yes, it's also an application for these materials.
Okay, thank you very much. Are there any other questions? Okay, if not, I thank again Philippe for the very nice and interesting seminar. And so I thank you, all of you, for attending. So goodbye.
Thank you very much for inviting me.
Okay, so goodbye and have a nice weekend.
You too, bye-bye.
Thank you, bye.
Thank you very much.